Hello everyone. So let's continue where we left off. So let me start a new page. So far what we did is, so I like to always keep the structure intact in whatever mathematical theories that I learn or create. So we defined the following structure. So we started out with Z, then we created the concept of congruences. So from that, we created the concept of congruences, and those things work on Z. Then from that, we created a set whose elements are congruence classes, and then we are kind of discovering the structure and how many elements does it have, etc., on those things. So why did we create Zn? Is just because it resembles the same kind of structure as Z, but it is finite, so we might want to we might get information from a finite set, or some information could be algebraic, could be geometric, etc., from Zn, and then import that information back to Z. So let's do that. So we didn't in the whole theory, we didn't yet discover how many elements does Zn have, and we want to see how can we classify those elements. So then we did we discovered that the elements, like the classes, are either disjoint or identical, but we don't know how many there exist. So in the following corollary, it will tell us how many exist, and then we can review what we did for this subsection, as we will be done. So we have the following corollary. (2.5) let n be bigger than 1, be an integer, and consider congruence modulo n and then we have each congruence class is given by all the possible remainders once you divide by n. So if a is an integer, we can always consider all the classes of a. So then that gives us all the possible congruence class, but we might get set being replicated because we see that we have this property of two congruence classes modulo n are either disjoint or identical. So we might get a process that repeats. So if a is any integer, and r is the remainder when a is divided by n, then the class of A is equal to the class of R. And the second thing, this we can use that information to figure out that there's only n distinct congruent classes when we take them with respect to modulo n. There are exactly n distinct congruences classes, namely 0, the class of 0, the class of 1, etc., all the way to the class of n minus 1. So let's prove those statements. But as you can see here, we started out, so let's just see the structure again. The structure is that we started out with Z, we defined congruence classes, we extracted some properties with respect to congruence classes, and then we used those properties to prove that, well, we first induced a new set from the congruence property that we have defined, or the congruence relation that we have defined, and this set has certain property that it kind of divides Z into a bunch of distinct elements, and not only that, we get that those distinct elements capture all of Z, and so you can create something finite from Z that has multiplication as well as division, as well as addition, as we will see in the next set of lectures. So that's the main point. So let's prove this corollary. So let A belong to Z, apply the division algorithm to A by n by dividing A by n. So by the division algorithm, we can write A as n multiplied by q plus r, with 0 less than r less than n. Therefore, A minus r is a multiple of n, which means A is congruent to r mod n. So by the previous theorem, we have that the class of A is equal to the class of R. All right, so that's one. And second thing, we consider all the following classes. We found out that the class of A is equal to R, where R runs between 0 and n minus 1. So we have to show that those things are distinct. So we will show that no two elements. So first, we show that no two elements S and T of 0 to n minus 1 are congruent. Modulo n. That will show directly that all the classes are distinct by the earlier theorem. So we have, if S and T are distinct elements that are between 0 and n minus 1, then we must have that either S is less than T or T is less than S. So assume one of the cases. So assume that T is a larger one. So we have that S is bigger than or equal to 0 and T is less than N. So then we have that hence T minus S is bigger than 0, but T minus S is less than N. So if we cannot divide N by T minus S and get a quotient. And so then that means that T minus S is not divisible by N. So they are not congruent. They are not congruent modulo N. So that means that N does not divide T minus S. So it follows that T is not congruent to S mod N. And so all the classes are distinct. So then it follows that the class of T is not equal to the class of S. And so that means all the classes from 0 to n minus 1 are distinct. And we are done. Yeah, so what we've discovered is that we can construct a set whose elements are congruence classes modulo n, and that is denoted by Zn, and we found that all of the elements are distinct, and that's a finite set, while the congruence, so the elements themselves are also sets that are infinite. So that's a cool construction in mathematics and happens all over math, is that you always can collapse something into something smaller, and then you can get information about that something smaller and then import it to the bigger thing that you're dealing with. So we'll see that with a lot of courses that I will be doing here on YouTube. So we have the following definition. The set of all congruence classes modulo n is denoted Zn, which is read Z mod n. So, as what is interesting about Zn is that we can represent its elements in different ways. Like the elements of Zn are themselves sets, and those sets can be the name structure of those sets can be represented in different way. So, for instance, the set generated by 2 is the same thing as the set generated by -1, which is the same thing as the set generated by 5, which is the same thing as 14 in Z3. Why is that? It's just because we have 2 is congruent to 5 mod 3, and 2 is congruent to -1 mod 3. 2 is congruent to 14 mod 3, and we can further invoke the earlier theorem that we proved. So yeah, I hope you guys enjoyed this video, and I will see you in the next one. But I just want to say that what we will do with all of my videos is that we'll analyze everything in a deep way. I like analyzing mathematics deeply. It gives you intuition as to what exactly you're studying, and it gives you a packet of problem-solving kits that you can apply not only through math, but through all of areas of your life. So yeah, I'll see you guys in the next video. Bye.